Lab 3, Separating Mixtures. Objectives. Recognize how the solubility of a salt varies with temperature. Demonstrate proficiency in fractional crystallization and in filtration. Solve the percentage of two salts recovered by fractional crystallization. Materials. Balance. Beaker tongs or hot net. Beakers for 150 milliliter. Bunsen burner or a hot plate. Filter paper. 100 milliliter graduated cylinder. Ice and rock salt. Sodium chloride and potassium nitrate solution, about 50 milliliters. Non-mercury thermometer, or the CBL unit, which we will mention at the bottom. Ring stand setup, rubber policeman, spatula, glass stirring rod, tray, tub, or pneumatic trough, vacuum filtration setup, or gravity filtration setup. In this case, we used a vacuum filtration setup. In place of a non-mercury thermometer, we will be using CBL unit. We did not use the graphing calculator. The vernier temperature probe goes along with the CBL unit. Don't forget your eye protection. This is also a lab where you may want to consider an apron and gloves. Safety procedures. We will need to pay close attention to all of the various safety procedures for this lab. Introduction. Your company has been contacted by a fireworks factory. A mislabeled container of sodium chloride, NaCl, was accidentally mixed with potassium nitrate, NKO3. Potassium nitrate is used as an oxidizer in fireworks to ensure that the fireworks burn thoroughly. The fireworks company wants your company to investigate ways they could separate the two compounds. They have provided an aqueous solution of the mixture for you to work with. The substances in a mixture can be separated by physical means. For example, if one of the substances dissolves in a liquid solvent but the other does not, the mixture can be filtered. The substance that dissolved will be carried through the filter by the solvent, but the other substance will not. Because both sodium chloride and potassium nitrate dissolve in water, filtering alone cannot separate them. However, there are differences in the way they dissolve. The graph in Figure A, which we'll see in a moment, shows the same amount of sodium chloride dissolving in water regardless of the temperature of the water. On the other hand, potassium nitrate is very soluble in warm water, but much less soluble at 0 degrees Celsius. Vacuum filtration setup. To set up vacuum filtration, screw an aspirator nozzle onto the hand pump. That's the kind we'll be using. Attach the other end of the plastic tubing to the side arm of the filter flask. Place a one-hole rubber stopper on the stem of the funnel and fit the stopper snugly into the neck of the filter flask as shown in Figure B. This would be Figure B. Place a piece of filter paper on the bottom of the funnel so that it is flat and covers all of the holes in the funnel. When you are ready, squeeze the hand pump using even repeated motions. This creates a vacuum which helps the filtering process go much faster. If the suction is working properly, the filter paper should be pulled against the bottom of the funnel, which results in a covering of all the holes. If the filter paper appears to have bubbles of air under it or is not centered well, turn the water off or stop squeezing the handle. Reposition the filter paper and begin again. As preparation, copy the data table below in your lab notebook. Be sure you have plenty of room for observations about each test. We actually have a copy of this in our binder, so all you really need to do is fill the data in on each line. Obtain 4 clean, dry 150 milliliter beakers and label them 1, 2, 3, and 4. Here are the instructions for our CBL. These are going to be a little bit altered because we did not use the graphing calculator. We merely used the CBL and the temperature probe. Connect the CBL to the graphing calculator with the unit-to-unit link cable using the I/O ports located on each unit. So we skipped that step. Connect the temperature probe to the CH port. We did that. Turn on the CBL, and then we didn't bother to start the program because we just used it as a probe. Set up your filtering apparatus. If you are using a Buchner funnel for vacuum filtration or a glass funnel for gravity filtration, follow the setup procedure under filtration technique option. We just went over our filtering apparatus, but there are different options in the printed lab. Measure the mass of a beaker to the nearest 0.01 gram and record the mass in your data table. Our mass for beaker 1 was 65.70 grams. Measure about 50 milliliters of the sodium chloride potassium nitrate solution into a graduated cylinder. Record the exact volume in your data table. Pour this mixture into beaker 1. We got exactly 50 milliliters. Using the temperature probe, measure the temperature of the mixture. Press trigger on the CBL to collect the temperature reading. This is what would happen if you were working with the graphing calculator. So our temperature before cooling was 29.7 degrees Celsius, which is a little much warmer than room temperature. But I had also just made the solution, so it was still probably a bit warm. Measure the mass of a piece of filter paper to the nearest 0.01 gram and record your mass in the data table. Our filter paper was 0.60 grams. Make an ice bath by filling a tray or tub or trough half full with ice. Add a handful of rock salt. The salt lowers the freezing point, so the water in the ice bath can cool to a lower temperature. Fill the ice bath with water until it is 3/4 full. Using a fresh supply of ice and distilled water, fill beaker 2. I forgot to stick a number 2 on that, but that's beaker 2. Fill beaker 2 half full with ice and add water. Do not add rock salt to this ice water mixture. You will use this water to wash your purified salt. Put beaker 1 with the NaCl KNO3 solution in the ice bath. Place the temperature probe in the solution to monitor the temperature. Stir the solution with the stirring rod while it cools. I also found it was easier to kind of swish the beaker around a little bit. You're going to be careful not to stir with the temperature probe. Lower the temperature of the mixture, the more the KNO3 will crystallize out of the solution. When the temperature nears 4 degrees Celsius, this is when, if you were using the graphing calculator, you would press trigger on the CBL. So this is the swishing motion I found worked a little better than the glass stirring rod. And as you can see, our temperature is getting lower and lower. And we're aiming for 4 degrees Celsius, so we are just a hair above it. Vacuum filtration. To prepare our filtering apparatus, the first thing we're going to do is pour approximately 50 milliliters of our ice-cold distilled water from beaker 2 through the filter paper. After it's gone through the funnel, we're going to empty the filter flask into the sink, reconnect everything, and then we'll begin filtering our solution by pouring the salt water mixture in beaker 1 into the funnel. We're going to use a rubber policeman, which is kind of like a little rubber spatula, to transfer all the cooled mixture into the funnel, especially any crystals that are visible. It may be helpful to add small amounts of ice-cold water from the beaker 2, to wash beaker 1 of any crystals. See, these crystals were left behind, so we had to not only scrape, but rinse a little bit. After the solution has passed through the funnel, We're going to wash the KNO3 residue by pouring a very small amount of ice cold water from beaker 2 over it. When this water has passed through the filter paper, we're going to carefully remove the tubing from the aspirator, empty the filtrate, which has passed through the filter paper and is now in the filter flask, into beaker 3. And then we'll move on to our next step. So this is how the filtering works. You work the hand pump, creates a vacuum, and it pulls the solution through not only the filter paper, but also all those little holes down into the flask, which catches our filtrate. And this is our filtrate from our first filtration. After you finish filtering, either use a hot plate or a Bunsen burner, here's our Bunsen burner, and a ring stand, ring, and wire gauze to heat beaker 3. When the liquid in beaker 3 begins to boil, we're going to continue to gently heat it until enough of the water has vaporized to decrease the volume to approximately 25 to 30 milliliters. Be sure to use beaker tongs. Remember that hot glassware does not always look hot. For a second filtration, we're going to allow the solution in beaker 3, the one that we just boiled and reduced, to cool. And then we're going to set it in an ice bath and stir it or swish it again until the temperature is approximately 4 degrees Celsius. And you'll notice this time that our remaining solution is much thicker. It's like a slurry at this point. So we've taken our washed and dried beaker 1, and we're going to get it out of our way after we have filled it with our filtrate. And then we're going to take our filter paper with the potassium nitrate out of our funnel from our filtering apparatus, and we're going to put it in a beaker. We're going to be very careful to avoid spilling any crystals. And this is kind of tricky because what was thin filter paper is now pretty thickly caked with a layer of potassium nitrate crystals. So next time I think I'm going to grab some forceps because this little wooden skewer was kind of tricky to use, but I also didn't want to stick my fingers all over it. Right into beaker 4. Now, in place of a drying oven, I'm using my regular household oven, but I am not turning on any heat. I'm simply placing the beaker inside overnight, and I'm turning on the light, which will produce just enough heat to dry any remaining liquid away from the crystals. So now how are we going to recover the sodium chloride? We're going to heat beaker 4, I should say beaker 1, sorry, on a hot plate or a Bunsen burner. That's our Bunsen burner. And we are going to heat it until the water begins to boil. The solution really begins to boil. We're going to continue to heat the beaker gently until all the water has vaporized and the salt appears dry. Turn off the burner and allow the beaker to cool. And then we're going to use our beaker tongs to remove it because it's still hot. We're going to measure the mass of the beaker with the sodium chloride to the nearest 0.01 gram, and we're going to record the mass in our data table. So this is what it looked like as it heated up. And as it continued to heat, it started to do that a little bit. So we had to adjust the flame and turn down the gas so it wasn't quite so hot, and I actually ended up raising the ring to get it a little further away from the hottest part of the flame. And this is where we ended up. But you see, it still popped around a little bit. It's a good thing for eye protection. "76 grams of sodium chloride was recovered, and as you can see, it is completely caked all over the inside, bottom, sides, everything. So So the next day, we pulled our beaker 1, that should say beaker 4, I mislabeled those, sorry. Beaker 1, 4, whatever, with the filter paper and the potassium nitrate from the oven. And we allowed it to cool, and then we went ahead and put it on our triple beam balance and recorded our mass, and recorded that right into our data table. So our mass was 73.10 grams. Now I went back and grabbed some screenshots for our temperature readings from both our first and second cooling and first and second filtration. So now we get towards the end here. We're going to clean all of our apparatus in the lab station. And once the mass of the sodium chloride's been determined, add water to dissolve the sodium chloride, and then you can just rinse that down the drain. But we're not going to put any potassium nitrate down the drain. You guys are going to dispose of that according to my directions. We're going to wash our hands thoroughly after the lab, and then we are going to make sure that our lab work is finished before we leave. So here is what we basically came up with. The masses of our beakers less the masses of our beakers with the salts in them less the mass of the beakers told us exactly how many grams of each of the 2 salts we were able to recover from the solution. So the first question in our analysis is to find the mass of the sodium chloride in our 50 milliliter sample by subtracting the mass of the empty beaker, and this is what we just did. We ended up with 10.3 grams. We're going to do the same thing with the potassium nitrate, and we ended up with 7.4. And then we're going to determine the total mass of the 2 salts, which was 17.70 grams. How many grams of potassium nitrate and sodium chloride would be found in a 1 liter sample of the solution? So a hint for this was for each substance, make a conversion factor by using the mass of the compound and the volume of the solution. So we're actually going to go over a couple different ways to solve the different types of math problems in this lab. So we have our sodium chloride at 10.30 grams per 50 milliliters, and we have our potassium nitrate at 7.40 grams per 50 milliliters. So 1 liter is 1,000 milliliters. So how many times does 50 milliliters go into 1,000? And of course, our answer is going to be 20. So if we choose to use that as our conversion factor, it's very much like balancing fractions. So if we start with 10.30 per 50, right? 10.30 grams over 50 milliliters, you can treat this like an algebra problem, and you can say, is something over 1,000? Well, what is it? We're going to use our conversion factor of 20. And in that case, we come out with 10.30 times 20 is 206. There are 206 grams of sodium chloride per liter. And to repeat that example down here, we use the same conversion factor for the potassium nitrate, and we end up with 148 grams of potassium nitrate per liter. Now, another way to solve this type of math problem is to use a traditional conversion factor like the type typically used in chemistry, engineering. It's actually pretty practical for many, many applications. So we're going to take the information we have, which is 10.30 grams per 50 milliliters, and that's what that division problem right there means. It's a fraction, it's also a division problem, and it can be read as 10.3 grams per 50 milliliters. So we want to get rid of the milliliters because the answer we need is grams per liter. So how do we do that? We need a conversion factor. And in this case, we're going to use 1,000 milliliters over 1 liter because that is equal to 1. 1,000 milliliters is a liter, and a liter is 1,000 milliliters. So this allows us to get rid of the milliliters because it's a conversion factor. So our milliliters disappear. We're left with grams on top and liters on bottom, which is what we want. So we're going to multiply straight across, and we're going to get 10,300 grams over 50 liters. And that, as a division problem, works out to 206 grams per liter, which is exactly the answer we got before. For the potassium nitrate, we follow the same steps. there's our first fraction. Here's our conversion factor. Multiply straight across. And work out that division problem. And you have 148 grams per liter, which is exactly what we had before. Analyzing graphs. Use the graph at the beginning of this exploration to determine how much of each compound would dissolve in 100 grams of water at room temperature and at the temperature of your ice water bath. Okay, so how do we tackle this one? Well, it helps to know that room temperature water is about 25 degrees Celsius. So that's going to hit right about there. At 25 degrees Celsius, about 35 grams of sodium chloride will dissolve in 100 grams of water. And about 32 grams of potassium nitrate will dissolve in the same volume of water at the same temperature. So there's our 4 degrees Celsius. So at 4 degrees Celsius, about 35 grams of sodium chloride, just the same as before, will dissolve in 100 grams of water. And about 300 grams of potassium nitrate will dissolve in the same volume of water at the same temperature. Calculate the percentage by mass of sodium chloride in the salt mixture. Calculate the percentage by mass of potassium nitrate in the salt mixture. So here's how we're going to do this. A mass percent formula looks like this. It's grams of solute divided by grams of solute plus solvent times 100. So a liter of water is 100 grams of water. So if we start with our sodium chloride at 206 grams of solute divided by the grams of solute plus the solvent, which is 206 plus 1,000, we get roughly 0.17. I'm going to round there. And then we're going to multiply that by 100 and get 17%. Same thing with the potassium nitrate. We're going to do the same exact equation. This time I got around 13%. I mean 13, so I 0.13, so I rounded and multiplied by 100 and we get 13%. The fireworks company has another 55 liters of salt mixture dissolved in water just like the sample you worked with. How many kilograms of each compound can the company expect to recover from this sample? You can use the answer you got from number 4 to help you with this question. And there's that answer again. So we can ask ourselves how many times does 1 liter go into 55 liters? 55 times, and we can work it this way. 206 grams in 1 liter is how many grams in 55 liters? And we get 11,333 grams. But it asked us how many kilograms. And 11,333 grams is 11.33 kilograms. So there are 11.33 kilograms of sodium chloride per 55 liter sample. We work the same problem over here. That's 148 grams to 1 liter. And that is going to give us how many grams in 55 liters? That's going to give us 8,140 grams, which means there are 8.14 kilograms of sodium chloride per 55 liter sample. So another way to do this, again, that conversion factor method we discussed earlier. There are 206 grams of sodium chloride per liter. So there's our grams per liter. What's our conversion factor going to be? We want to get rid of grams because we need kilograms per liter. So we'll put 1,000 grams on the bottom and a kilogram on top because that equals 1. And also, we need 55 of those kilograms. So if we go ahead and multiply straight across, we're going to get rid of the grams, and we're going to end up with 11,330 kilograms over 1,000 liters, which once again is 11.33 kilograms per liter. Same thing on the bottom, 148 grams over 1 liter, multiplied by our conversion factor, multiplied by the fact that we need 55 of those liters. We're going to get rid of the grams, and 8,140 kilograms per 1,000 liters, or 8.14 kilograms per liter. Evaluating methods use the graph shown at the beginning of this lab to estimate how much potassium nitrate could still be contaminating the sodium chloride you recovered. So how we're going to do this is we're going to consider that we did our recovery at 4 degrees Celsius. And earlier we determined that 35 grams of sodium chloride will dissolve in 100 grams of water. And we know that there were 206 grams of sodium chloride per liter of our sample. So that means if we take our 1,000 gram / 1 liter sample and knock that down to 100 grams, it's going to give us 20.6 grams of sodium chloride per 100 grams of our sample. The same thing will be true of our potassium nitrate, and that will bring us to 14.8 grams of sodium chloride per 100 grams of our sample. So if we have 20.6 grams of sodium chloride in our 100 gram sample, but it was capable of dissolving 35 grams of sodium chloride in our 100 gram sample, then we know that 35 grams minus 20.6 grams is 14.4 grams. And that's where our measurement is off. So that means that 14.4 grams of potassium nitrate may still have been contaminating our sample. 14.4 grams of potassium nitrate may have contaminated our sample. That's a lot. So what happened? Well, I hypothesized that this is the reason our sodium chloride to potassium nitrate ratio is so off. That's sodium chloride. As the solution reduced in volume, it became so viscous that the boiling process caused it to bubble and pop out of the beaker. If we could have collected this and included the mass of this lost portion of the sample, it would increase the ratio of sodium chloride, thereby decreasing the ratio of potassium nitrate in our calculations, and this would result in a higher percentage of mass for the potassium nitrate. And congratulations, you've made it to the end of this lab.